Okay, I think we're recording. There we go. So we are in the second week of kind of like a 4-week part of analytics. And last week we focused on just some like intro and advanced kind of capacities for doing regression in R. So that was just kind of basic, simple linear, multiple regression, moderation, and simple slopes analyses. And so we went a little bit past time just because I really wanted to get through how to do simple slopes, kind of using the Preacher et al. Simple slopes analysis with regions of significance. So if you weren't able to stay on with us last week, the video is up and available, and so you can grab that, follow up. Sorry, I'm getting like notifications on the video. There we go. And so as I was thinking about what to do this week, I know I had talked about kind of doing dominance analysis and thinking about a few other analytics, but I decided to pivot from that to instead kind of do an introduction to quantile regression. And so there's at least a couple people on here who have been working with me for a little bit of time. And one of the places as a methodologist that I've been really pressing in regression for the last maybe 8 years or so is on thinking about quantile regression and how that can be used both complementary and supplementary to kind of conventional ordinary least squares analysis. And so we'll spend about an hour kind of going through some basic theoretical underpinnings, like really basic, and then kind of get to the modeling. And I've posted 2 papers in the channel that you can read to give you maybe some foundational insights into quantile regression if you're not familiar with the technique. One is the original paper by Koenker, one of the original papers where he really kind of unpacks the analysis, how it's different, and I think there's some of the proofs there if you're into that sort of thing. And then another is a paper I published with a colleague of mine, Jessica Logan, who's at Ohio State. She's a methodologist. There, we were in grad school together, and we wrote this paper. I think when we were in grad school for a little bit, just as a very applied introduction to scientists in social and education sciences. So that paper is up there that you can read. So I find that a lot of people ask lots of questions about quantile regression. They're curious about it. When they start learning about its utility, people really jump on board with the ideas and what it affords us the ability to do analytically. And so Keenan's joining, I think, for the 3rd time related to quantile regression. Nice strong representation for Wu-Tang. And so we're going to just jump into high-level discussion for just a couple minutes about quantile regression. We'll get into the analytics, and then if folks have questions, again, this is the first time I've done something like this, of just like I'm talking to a camera, and we have a large number of people on here. So as people ask questions, hopefully there might be some time at the end. I'm very poor at gauging the amount of time it takes to go through these things. I'll try to answer questions because quantile is one of those things of like it really warps your thinking a little bit in terms of what it does. So if you've got questions, put them in there and I'll try to address them either in the midst of conversations as as like one of my usual rabbit trails, or we'll try to get to it at the end or otherwise. So let me jump into talking about or thinking about what quantile regression is, but just kind of showing this plot. And this is one that I tend to use pretty frequently. And so I pulled some data from the NBA and was looking at Steph Curry in his first 7 seasons in the NBA and looking at the relation between his 3-point field goal percentage accuracy and his total points per game. And so the idea was, can we predict how much he's going to score based on his accuracy in scoring? And so we just, I took the data, and you can, in a traditional kind of ordinary least squares, you can get this line of fit that we can ultimately be able to, through whether it's just a correlation, through a simple linear regression with a standardized coefficient, we get an estimate of the strength of the relation between shooting percentage and points per game. And what you basically get from this is a line that fits this way, and it kind of corresponds to a correlation of like 0.46. So there's about a moderate association between his three-point shooting accuracy and points per game. But what's actually really interesting about this, I want to see if I can actually overlay the plot here. Nope, it's not going to do it. Is if I was to actually draw a line, I'll actually draw the line here. If we look at different levels of points per game, you can actually see that at different levels of Y, right? So at different levels of the distribution of Y, there is differential variability in X, right? So at the very low points per game, you can see there's a fairly wide spread of his accuracy. So if Steph scored, let's say about 8 points in a game, his associated field goal accuracy for three-pointers might have ranged from 0 to 100%. But as you kind of move up the distribution, you can see there's still a pretty wide range of variability that, depending on his points per game, there's variability in his shooting accuracy. But as you get to the top here, you can see that the shooting accuracy band becomes a bit narrower, right? So there's kind of less variability up here than there is, right? So if we kind of fit a line there, there's less variability up here. When he shoots 50 points per game, he is highly accurate, right? He's between 60 and 75% accuracy on his three-point shooting when he scores about 50 points. But when he's scoring around 10 points per game, he's either getting it or he's not at all. And, there's some in the middle. And so that could be suggestive of the fact that this line of best fit, it's a line of best fit in a conditional means framework. Okay, and so if you're not familiar with conditional means modeling, conditional means modeling is pretty much what governs pretty much all regression that we do. And so whether we're doing kind of Pearson correlations, multi-level modeling, structural equation modeling, these are all conditional means-based analyses, which means that the estimates of intercepts and slopes are kind of minimizing sums of squares and estimates as a function of the conditional mean of the distribution of the outcome. And that has some important implications for us. So when we think about a conditional mean of Y given X, we're talking about minimizing the sum of squared kind of given those relations, but we can actually broaden the conditional expectation of Y given X that's not just on the mean. So we could say, what's the conditional mean of Y given X? But we could also kind of think about central tendency, right? And so if you have means, you also have medians and modes. And so we could kind of broaden the idea of correlations and regression to say, instead of asking a question about the conditional mean of Y given X, we could say something like, well, what's the conditional median of Y given X? And so in that case, we're kind of like minimizing an expected absolute error instead of an expected squared error, but it's at the median of Y, not the mean of Y. No one does conditional mode models because modes are, as I like to joke, modes are the saddest measure of central tendency. They rarely get any love. And so if we think about some of the things we take for granted in our modeling, conditional means models are kind of heuristical in some ways. Like we do that because it allows us to make certain model assumptions. It allows us to make certain data assumptions. But when you actually just like do a lot of data simulations, you find that under certain circumstances, a lot of different assumptions of different models don't hold. So it's the same kind of thing with regression. If we are given a set of observations for X and Y, we can kind of pose a hypothetical relation between X and Y. And we can get things like unconditional means, right? So if we have, like we've been measuring math achievement and SES, if we hypothesize the relation between math and SES, we can think about things like the unconditional mean of Y. So we could say, well, what is the mean of math achievement unrelated to SES? We could also ask, what is the unconditional median of math achievement? right? Those are just simple descriptive statistics when we say unconditional, because we're not conditioning our estimate of math achievement on any independent variable. We're not trying to say, what is the average estimate of y given x? When we do descriptive statistics, we're just saying, what is the mean or the median or the mode or the standard deviation of this variable? So if we have kind of bivariate relations, we could say, well, what are the unconditional means of each of these variables? But we could also say, what are the conditional means of y given x? So we could say, what's the conditional mean math achievement given SES, or given a dichotomous variable of sex or minority status. So in the same way that we can ask kind of questions about the unconditional mean and median of math achievements, we could also ask about the conditional mean or the conditional median of y given Rx. So we can ask about an unconditional mean or median or mode of math achievement, but we could also think about what's the conditional mean of math achievement given SES, what's the conditional median of math achievement given SES, and we could say what's the conditional mode of math achievement given SES, right? And so what that's really doing is broadening at a very basic level our descriptive questions. We're moving from unconditional means and medians of math achievement to conditional means and medians of math achievement given some variable. So if we apply that to this plot right here, we could say independently, what is the unconditional mean of points per game? On average, how many points per game does Steph Curry score? And we could separately say, on average, what's Steph's three-point field goal percentage? We could then also say, what's the conditional points per game that he scores given his three-point shooting accuracy? But then that too could get broadened to not just say, what's the conditional mean of his points per game given shooting accuracy? We could say, what's the conditional median points per game given his shooting accuracy? The reason I'm setting that foundation is once you move from a mean to a median or a mode, you're really just talking about different points of a distribution for your outcome, whether it's points per game or, like in the data we've been working with, math achievement, right? And so if we say average math achievement, median math achievement, mode math achievement, and then we say what's the conditional points per game given his shooting accuracy, or what's the conditional median given shooting accuracy, we can actually get a broader perspective of the distribution of points per game or math achievement. It doesn't have to just be the mean of math achievement or the median of math achievement. It could be what we would call the conditional tau, okay? So rather than saying at the condition, what is the conditional mean of points per game given shooting accuracy, or what's the conditional median of points per game shooting accuracy, we could say, what's the conditional tau of points per game given shooting accuracy, where tau is any point of the distribution along the distribution of points per game. And so you could actually come up with the expected y given x when you condition at something like the 10th percentile rather than, let's say, the 50th percentile. So if you have a normal distribution, right, the mean, the median, the mode are all equal. And so the mean would be the 50th percentile, and the mean would be equal to, again, the median. You could actually say, rather than conditioning or trying to understand the expected points per game conditional on the average points per game, you could do it at something like a 10th percentile to be able to say, does the relation between shooting accuracy and points per game vary based on Steph's actual points per game? And so when you think about it that way, it gives us a different way to be able to model these data, such that, when we return to that first example of, if I kind of overlay this line here where we have much more variability in X controlling for the level of Y, it could be that there is a weaker relation between shooting accuracy and points per game at lower levels, when we condition on lower levels of points per game, compared to, I'm going to actually see if I can copy this line. If we were to come up with a conditional estimate of Y given points per game up here. So there's less variance in X given y right here compared to down here. So what that could mean is that at conditionally higher levels of points per game, there is a stronger predictive relation between shooting accuracy and point production than at lower levels. Okay, so this might be the line of best fit when we consider trying to minimize the sum of squares conditional on the mean. But when we actually condition at other points of the distribution, we may find the coefficient for x is lower or smaller here, and it could be larger here. Again, the variance is not as large here. It's much wider here, suggesting that the line of fit could actually be weaker down here and stronger up here. So that is a overly, I know it sounds super complex, and it is, but that's just a high level overview of what something like quantile regression tries to do. The way I tend to talk about it is that if we think about the way we frame our research questions, which is very broadly, what is the relation between X and Y? Quantile regression kind of like broadens the way we can ask our question, which is like, what is the strength of the relation between X and Y given different levels of Y? Or better stated, for whom is the relation between X and Y stronger or weaker? So it's kind of like more of a telescopic analysis where conditional means might be a little bit more microscopic. And so conditional means kind of gives you one intercept and one slope. Quantile regression lets you get many intercepts, many slopes along different points of the conditional distribution of the outcome. So with that as a little bit of a framing device, I'm going to jump in just to kind of show you what this actually looks like. I don't know if that's a high five or if that's a question, but Keenan, if you want to populate a question in the meeting chat, you can put that there, and I'll try to get to it either during or later. So if you've got your R window open, if you got your code to follow along, I would recommend installing these 4 packages. We're gonna they help us do just some different things throughout. So I'm gonna read in our data, and so this is where, again, I'm using the tidyverse read-in. So that way, when I call the table, it produces something that's a tibble, and that lets me be able to see the data quite a bit more in a bit more user-friendly way, at least for me. So what I'm going to do is start, and we've done this a little bit before, but just as a refresher, if I was just to read in the data, this is where we have, again, math achievement, SES. We've got 2 dichotomous variables for sex and minority status, and then we have 2 ID variables. We've got a student ID and we have a school ID. Here's where I'm just running supposed to be running there we go. I think it's populating. Just a scatter plot looking at kind of pairs among the different variables. But of course, when I want it to be populating, it's not going to actually populate. So, well, what would show up and what may show up, hopefully in a few moments, is that using the pairs analysis, oh, there we go, and it's giving me a womp womp right there. So what it would show is just a matrix where it has all of the variables, and it would be showing the scatter among all the different pairs of the measures. But the problem is that when we read in this data set, right, there we go, look at that. It just needed to think. So this is showing the scatter among all the measures, but part of the problem is when we first read in our data set, it has 2 ID variables. So if we wanted pairs among all measures that are within the data set, we need to remove those. So with the tidyverse language, right, I'm just creating a new data set called HSB1, and I'm keeping everything but, remember the negative sign means everything but in some way. So I'm saying select all the measures except for student ID and school ID. And when I do that, what it's going to end up generating is a scatter plot for the relations among these 4 variables, and it's going to drop the IDs, right? So you can get, here's where we can see, here's the relation between math achievement and SES. And so this allows us to kind of get a quick sense for what's happening in the data. Some very low key and quick to run types of histograms like we did last week. And again, for those who are maybe new or saying, hey, there's better ways to kind of generate these plots, the answer is kind of yes and amen. We're going to be getting into plots in 3 weeks from today. I'm just showing right now just simple ways that we can get to those without using ggplot, but we will be doing the true and better plotting with ggplot in a few weeks. So if I wanted to just quickly check the distributions, you can see we've got a little, yes, that looks awesome, Amy. We've got a nice distribution of math achievement. You can see there might be a little bit of skew there, not too bad. And then you can do the same thing with SES. We're getting a distribution there. Might be a few outliers there, but might not be exerting excessive influence on the data here. But as we start to dig into, you know, as we look beyond kind of the univariates in terms of the figures and the characteristics, we can start thinking about the bivariate relations between SES and math achievement. Again, this is related to what we did last week. We're just going to add some nuance to that. So you can load up the lattice and the lattice extra packages. And what this is going to do here, this is just a simple XY plot. And so this is just saying regress math achievement on SES. And then for this one, I am only estimating kind of the median association between SES and math achievement. And so because these data are approximately bivariate normal, then we can see that this line of fit is going to look pretty close to what we would generate for the conditional means model. You know, and so this corresponds to, I think, is like a 0.7 correlation. I can't remember. I could run it, but I'm not going to. So we can do something super basic like this, just to understand the nature of the relation among the variables. So you can see kind of down here, maybe there's a little bit more spread along SES at math achievement, or between like 2 and 7. A little bit more spread here, a little bit of a tighter distribution just in terms of the spread of SES given math achievement. So there might be some places where there are stronger or weaker relations between SES and math achievement given different levels of math achievement. But we could do a little bit more plotting. So that's where, in this plot called kind of extra, is where I'm actually going to overlay different taus. So tau, is there a way to turn? Yeah, there is, Mike. We could talk. We'll talk about that one later. And so you can actually overlay different taus, where tau is basically quantile, right? So if we're thinking about conditional means models, we say the mean. If we say a median model, we say the median. But if we want to think about a different point of the distribution, we call it a tau. And so you could think of tau kind of like conceptually, it's conceptually like a percentile, right? And so percentile is a way to be able to kind of like demark a place on the distribution at which a certain percentage of people are below and a certain percentage of people are above. And so that's kind of like what a quantile is. So you can keep in your mind, it's not the exact same thing because it's not an exact rank. Yeah, I don't know about, I know what you mean about nomothetic and idiographic. So I think very broad. So Keenan is basically asking a question about the extent to which kind of, quantile regression could be viewed as a bridge between nomothetic and idiographic. So you are using all the group information, but you're conditioning along different points of the distribution, and it's not really about individuals, right? It's a way to be able to highlight the variability that might allow you to start getting more to idiographic based inferences, but it's not an idiographic based analysis. Because when we, these relations we get regression coefficients and we can come up with predicted scores, but those predicted scores end up being kind of the same given equal characteristics. There's probably a smarter answer to that, but that's just my off the cuff reaction. Anywho, so what you can see from this line is when we actually overlay different quantiles to this, you can see that some have kind of a stronger angle than the other, right? So you can see in the middle here that the slope of the line is a bit stronger in some cases, but then down here, this blue line has a bit of a lower slope. This magenta line has a little bit of a weaker slope there. And so we can unpack this a little bit further, try to understand it. So we've got the basic plot, the extra, and then we've got the Kanye plot, which is like super extra. And so here we can get not only the plot with the lines, but we can also kind of label those lines according to the quantile. That helps us better unpack kind of what's happening here. So what you can see is that when we condition the scatter relations along different levels of math achievement, we're not finding that the slopes that quantify the relation between SES and math achievement are strictly the same. There are some stronger relations and there are some weaker relations. So we can actually unpack that formally, like the scatter plot and the lines are helping us. We can formalize these things a little bit more by running the analyses. So if we start with the simple linear regression, this is where I'm just creating an object called OLS and I'm running an OLS model regressing math achievement on SES. What it's telling us is that the mean math achievement given SES equals 0 is 12.74, and for every kind of unit change in SES, we get a 3-point increase in math achievement. All right, so I want to. I'm trying to think if this is the. All right, here's what I want. Before I introduce quantile regression, I actually want to put in a different. I want to put in the dichotomous variable because I want to explain an alternative way to interpret those coefficients. All right, so here's where we put in sex as a dichotomous variable. And so what this is saying is, right, that the mean math achievement when female equals 0, right, is 13.64. And for every unit change in the female variable, right, as you go from 0 to 1, math decreases by 1.7 units, okay? And so the substantive interpretation of that is that because female is a dichotomous variable, is that the average estimated math achievement for males is 3.64, and the estimated average math achievement for females is 1.7 points lower than males. So that's, one of the conventional ways that we interpret our slope coefficients is in those kind of expected changes in Y given some of these unit values in X. But I want to give you an alternative explanation or interpretive mechanism for these kinds of relations that is accurate. It's going to sound wonky. It's a little bit longer, but it's going to help us as we pivot to quantile regression. So yes, we can say the average estimated math achievement for males is 13.6, or we could just say the intercept, the estimated math achievement where female equals 0 is 13.64, and for every unit change in sex, there is a decrease in math achievement. Another way to interpret this is to say at the conditional mean of math achievement, the gap in estimated math achievement between males and females is 1.7 points. Okay, I'll say that again. At the conditional mean of math achievement, the gap in math achievement between males and females is 1.7 points. And so you can tell that there's a difference between those different mechanisms. Are people having an issue with the QuantReg package? I'm seeing some things there that seem wonky. So if anyone else is having an issue with that, I guess, if anyone is not having a quantile regression package issue, if you could maybe help folks out who are on there. You may need to load the package first. If you're not using the function RQ, you may need to do the library QuantReg. Yeah, there you go. Sorry about that. So we can interpret this as for every unit change in the independent variable, there is a change in the estimated dependent variable. Or we could say at the conditional mean of the dependent variable, there is a gap in the value of the dependent variable for people who are at different levels of X. Okay, I'll say it one more time, and I know I keep saying it, but it's going to be really helpful when we get to quantile regression. We could say that this is these results are saying that at the conditional mean of math achievement, the gap in math achievement between males and females is 1.7 points, which means the conditional mean of math achievement here is 13.6. That's for males, and the gap between males and females is 1.7 points. Okay, so that's a different way that we can interpret intercept and slope coefficients in conditional means models. It's different than what we're taught. We usually think about the reciprocal XY relations, but when we say that our slope coefficients are actually representing a gap in estimated Y between two different levels of X, right? The mean of X and a unit change in X, it's going to help us right now. So if you load up the QuantReg package, what this is doing on line 59 here is this is estimating the relation between math achievement and SES conditional on the 0.5 quantile of Y, which is the median. So this OLS analysis is implicitly doing a conditional means model where it's conditioning the relations, or it's coming up with the conditional mean of Y given X. And this is going to come up with the conditional median of Y given X because I specified the 0.5 tau. Tau is quantile. So if you run that, what you can see here is a bit of a difference between the mean and the median. Okay, in the OLS regression, and I'm actually going to run this with because I did female here, I'll run it with female here. So just change this to female, and this will probably help with some interpretive mechanisms as well. All right, so for the OLS regression, we said that the gap in math achievement at the conditional mean of math achievement is 1.7 points between males and females. When we do the conditional median model, where we're specifying 0.5, we find that the gap is a little bit wider. So it's not at the mean of math achievement, males and females differ by about 1.7 points. But when we condition those relations at the median of math achievement, the gap is a little bit larger, but not that much, right? So the gap in estimated math achievement, when you condition at the median of math achievement, the gap in performance between males and females is 2.1 points. But at the conditional mean of math achievement, the gap in math between males and females is 1.7 points. And so in some ways, we could say the gap between males and females is smaller when you condition on the mean versus the median. There's a slightly larger gap in math when you condition on the median of math versus the mean of math. All right, so so we could actually look at more than 1 point within the same analysis. So what we can do is broaden our taus, where we pass a vector through this analysis. So on line 75 here, we're saying run the same analysis, but do it for 3 different quantiles. This is the 0.25, which would be like the 25th percentile, the 0.5, which is the median, or like the 50th percentile, and then 0.75, which is like a 75th percentile. But these are conditional estimates, which is why it's not the same as a percentile rank, right? Percentile ranks are unconditional. That's just based on the variable. These are conditional estimates. So what this is actually doing when you run this one quantile regression, it looks like it's running 1. It's actually running 3 within the same model. So when you run that code, what you can see here is it's doing a quantile regression with a result at the 0.25 quantile, the 0.5 quantile, and the 0.75 quantile. And what you can see with this result, and this is where we're doing, sorry, I did SES again instead of, there we go. You can see that the gaps differ depending on where we condition the relations. And so if we were to say, what is the estimated gap in math achievement between males and females when we condition our results not on the mean, but on like the 25th percentile of math achievement, the gap is 1.58 points. But if we condition at a higher level of math achievement, we find that the gap is larger. So if we think about the lower end of the distribution of math, at conditionally lower levels of math, there is a smaller gap between males and females compared to at higher levels of math. All right, so what this would be saying in a more formal definition or interpretation, the way I explained it before, is that at the 0.2, at the conditional 0.2 quantile of math achievement, the gap in math achievement between males and females is 1.59 points. So by interpreting the coefficients this way, it actually gives us a little bit more symmetry between what we interpret in OLS and what we interpret in quantile regression. If we stick with the as you change in y by some value, or as you change by x in some value, you change by y in some value, that doesn't necessarily lend itself to an easy interpretation in quantile regression. Because if we were to say, as you increase, as you move from male to female, math achievement increases or changes by 1.59 points, it's weird to think about that because some people might say, well, doesn't that change your quantile if you were higher? And that gets back to Keenan's question of like, is this a little bit more idiographic than nomothetic? And part of the answer there is no, because we're not talking about like individuals. We're talking about estimates within we're talking about estimation. And we're talking about the group and not the individuals. And so if we instead talk about what is the gap in estimated outcomes at conditional tau levels of the outcome, given different levels of X, we're allowed to have a kind of a consistent interpretation between OLS regression and quantile regression. I know this is complex and it's super wonky to think about. And so I would encourage you to like, read these couple papers that I put up there, go back, listen to this video. Jessica Logan actually has a fantastic, I think it's like a 2 or 3 hour lecture that she has online. I have one as well that I can make freely available. It's like, it's actually 6 hours, where it's 3 hours of theory and 3 hours of analyses. I'm trying to bring that all into an hour introduction. So if anyone's interested in those kinds of materials, I'm happy to post that in addition to this video. So we can actually go from, so we went from 1 quantile in 0.5 to now we have 3 quantiles being estimated. And you can actually add a lot more quantiles. And so quantiles range from approximately 0 to 1. You can have them in increments of 0.01 or 001 or 00001. But the issue there is the data don't know where they've come from, and they don't know where they're going. And so you have to estimate your quantiles with some type of heuristic or interpretive mechanism in mind. So again, when we think about like quantiles being like percentiles, it's easier to think about like the 5th, the 10th, the 15th percentile, or really the 1st to the 99th percentile. That gives a better kind of interpretive mechanism or kind of like hang your hat on something in order to try to think about where these models are being conditioned. So this one is an example of doing these in increments of 0.05. And so you can see I both get estimates and warnings. So this warning right here, I actually have a little note about this up here. You may get this because of the way that the standard errors are being estimated. And so the default for this is it's the NID. And so you will tend to get this error sometimes based on if you have like, I think it's like a fairly large, I think it's if you have a fairly large sample size, these things are you can skip over this. Child age and height. Yeah, here's the thing with age and height though, is I think that that's more of a piecewise regression than, so Mike is kind of saying, is child age and height a good example for it? And so part of the reason, so it could be, but part of the reason it might not be is that you actually get, so right here's the CDC charts where the conditioning is actually maybe happening on age and not height. So you're not conditioning it on height. It's more that like at a level of X. So at age 13, you hit an asymptote of growth. So you could do a piecewise regression that you still could do a piecewise regression and a quantile regression, but age and height might be more of a piecewise type of analogy. But I do use that for quantile regression. Sorry, I know I'm rabbit trailing. So in general, you can kind of like skip this warning message, but you may want to check to see if it is reflecting some type of like model misspecification. So you can do increments of 0.05 for the quantiles. And there's other ways that you can actually kind of like embed your quantiles into this tau expression. So one is you can pass a vector through and you can actually list it out in terms of like, 0.25, 0.5, 0.75. You can do it in increments of 0.05. You could do it in increments of 0.01. The other thing you can actually do is specify your quantiles as an object. And so here's one where I create an object called meh. And meh is a vector that has 3 quantiles or 3 values in it, right? 0.25, 0.5, and 0.75. Yeah, so someone's asking, what's the advantage of quantile regression over OLS? And I'm going to show it to you in a couple minutes. It'll be, right now I'm kind of going through the steps, but then I'll actually show you the tangible outworking of why quantile regression is more powerful than OLS. So if you create an object called meh, you could actually then put that vector of values in place for tau. You don't have to list everything out. You could just say, call meh a vector of three estimates. You can run it, and you will see you get three different quantile regressions being done and reported here. I can do the same thing with this original vector of 0.05 to 0.95. I can just call the vector meh as an object. I can then run it, summarize it, and then I'm getting all of those values for every single quantile. Maybe I don't want to specify it as a full vector. I just want to be like a sequence of values. Well, I can get the 0.05 to 0.95 by saying sequence numbers 1 through 19 and divide it by 20, right? So if I take 1 divided by 20, 2 divided by 20, all the way up to 19 divided by 20, then I can get estimates of quantiles from 0.05 through 0.95. I can do the same thing if I just want 10 quantiles, 0.1 through 0.9. Okay, so there's basically there's super flexible ways to do this. The last one I'll show you is you can also use a sequence statement. You can say tau is equal to a sequence where I want a range of 0.05 to 0.95 by 0.05 increments, or I want a range of quantiles from 0.05 to 0.95 by 0.01 increments. So this is going to give the exact same result as before. It's doing quantiles in order from 0.05 to 0.95 in increments of 0.05. So that's pretty easy. For the sake of time, I'm going to jump ahead to some of the interesting results and to some of the questions that people are asking. What I have in here, just so you know, like starting in line 107, this is kind of showing the different types of standard errors that you can be using in your summary statement. That may have different implications based on the number of predictors that you have and the number and the sample size that you have. And so you can do some reading on your own. You can also look at the trade-off in terms of what your standard errors look like when you use different types. There's bootstrap methods as well. But for now, I'm going to jump down to line 157, which is where I start showing plots. So if I take QM10, which is QM10 is line 108. This is just math achievement and SES in increments of 0.05 quantiles. If I plot this, this is where you actually can see the benefit of quantile regression. And so you're getting two different plots here. Up here is an estimated intercept plot for each of your quantiles. Each dot is a quantile, and then the line is sort of like a mini interpolation between the values. So you can see this is the estimated math achievement conditional on the 0.05 quantile, 0.1. Is this 0.1? 5, 10. Yeah, so 5, 0.05, 0.1, 0.15, 0.2, all the way up to 0.95. And so this is falling, along the lines of expectation, right? At lower levels of math achievement, there should be lower math achievement. At higher levels of math achievement, there should be higher math achievement. When SES equals 0, right, this is just the distribution of math scores. So this is actually showing us exactly what we would expect. Low levels at low quantiles, we get low math, high quantiles, high math. So this is actually the estimate of your intercept. These are your quantiles. So this is 0.05 to 0.95. And so it kind of has 0.2, 0.4, 0.6, 0.8 quantiles by default. This red line here, this is your OLS estimate. So if I do, this is now doing, this is going to do, yeah, it is. Probably faster to type it, but I'm not. There we go. Yes, this is very good for skewed data. There are certain assumptions on on quantile regression, but it doesn't assume kind of constant variance or kind of normality in the way that OLS does. And so that's one of the reasons that quantile regression is more flexible. Okay, so what you can see here is that the estimated intercept in OLS is 12.7. That's what's being plotted right here. This bar represents the intercept in an OLS, and here we get an estimate. 3.18 is the estimated slope in OLS. That's what we're getting right here. Okay, so within quantile regression, you get the estimated intercept and slope from an OLS. What this is showing, again, rightly, is that at 0.05 quantile of math achievement, you get a different estimate of math achievement. It should not be 12.7. The estimated math achievement at the conditional 0.05 quantile of math should be about 1 or 2. But at the 0.5 quantile, which is right here, right? So this is the 0.5 quantile, which is the median. And in a bivariate normal distribution, remember, the median is equal to the mean. And so that's why if we drew a line right here down, it's going to correspond to 0.5. And you can see how close estimated median math achievement given SES is almost identical to the OLS value right here, right? This circle right here is right on that red line. And so the conditional median estimate of math achievement is pretty much identical to the conditional mean math achievement given SES. Where quantile regression then is especially powerful is on the slopes, okay? So if we were to say that the relation between SES and math achievement is strong, that as you increase SES by a unit, you get a bump, or expected math increases by 3.18. That would be reasonable. But what it actually does is obfuscates the actual relations between SES and math achievement, okay? Because you're not seeing my screen. Is that the same? Are people not able to see my screen right now? Sorry, we're going to pause for a second because folks are saying they can't see. All right. Give it 1 second. Sorry, there's some technical difficulties here, I guess. If there's someone on audio, can people hear me?
I could hear you, and I could see your screen.
Oh, okay. Thank you. All right. So for some reason, my Teams is frozen. Video is working, but I don't know what's happening.
So this is Amy. What's happening for me is it's freezing up a lot, but I can see and hear you. Like, I just can't seem to interact with the system, but I can still see and hear you.
Okay, let's see. Are people able to see the screen again now?
Yes, I can see it.
Okay. Yeah, sorry about that. Not sure what happened there. I don't know where I trailed off, but the point is that, so I think where I was getting to was on this slope plot is really where you can see the power of quantile regression. Because if we were to say that the estimated effect of SES on math achievement was 3.18, that might be good at the conditional mean of math achievement, but it's actually both over and underestimating the relations between SES and math achievement depending on level of math achievement, right? So you can see at higher levels of math achievement up here, the SES does not have as strong of an impact on higher levels of math achievement. And that's the same at the lower end of the distribution. So if you have high math achievement, low math achievement, the impact of SES is not as strong as when you are in the middle of the distribution of math achievement. So if you're kind of average in terms of your math achievement, SES tends to be pretty strongly predictive of your math achievement. But if you have higher or lower, your SES doesn't discriminate among levels of math achievement. There isn't as much of a difference whether you are higher SES or lower SES. It's not as strongly predictive of your math achievement. So a different way to state that is that at conditionally higher levels of math achievement, there is a smaller gap in math achievement between high SES versus average SES, or average SES versus low SES. There is not as much of an impact in SES at higher or lower levels. But if you are at the let's say the median of the distribution, the impact of SES on math achievement is much stronger. And so this is a way when you see these kind of like bell-shaped curves or U-shaped curves, they're showing that there is a differential, or in a fancier way of saying, there's a heteroscedastic relation between SES and math achievement conditional on your SES. So what I want to be able to do, because we've got like maybe 10 or 15 minutes, is kind of show a few different things. So this code right here just shows you how you can better isolate your plots. So you could do a general plot statement, but if you do parm for parameter, you can isolate SES. So here you can see that like at like the 0.5 quantile, the slope coefficient is closer to 4 compared to 3.18 in OLS. Whereas at like the 0.9 quantile, the coefficient is half the size, right? And so the predictive strength is half as strong at higher and lower levels of math achievement compared to the middle of the distribution. And so what we would say about the importance of SES is very different if you have higher or lower math achievement. You can then also condition, get the plot separately for the intercept. So this is just useful for plots. So what this does not show is the amount of non-overlap between quantile regression and OLS. And so the way you can do that is by using not just plot QM10, it's not just plotting the object, you have to say plot summary QM10. And so what you can see here is you start to get the bands for both the OLS and the SES. Now what this does for us is it gives us an empirical test of the extent to which the slope coefficients from quantile regression are significantly different from OLS. So here we can say that at these levels of Y, so from about the 0.15 quantile to the 0.3 quantile, the slopes, the estimated slopes for SES are equivalent to what we would estimate in OLS, because this is the confidence interval for the OLS slope. This gray band is the confidence interval for the SES slope and regression. So where those confidence intervals overlap, we would say the estimates are not statistically distinguished from each other. But anything where there is not overlap between confidence intervals tells us that this estimate here, for example, is statistically different from this estimate here. So if we were to condition our slope coefficients at the 0.5 quantile, we can say that the effect of SES on math achievement is significantly stronger at the 0.5 quantile of Y compared to the conditional mean of Y. And we can do that again for any place along the distribution where the confidence intervals don't overlap. So what this tells us is that while for a small range of levels of math achievement, the slope coefficients are in quantile regression are in line with OLS. For the vast majority, the OLS estimate of SES under or overestimates the actual strength of the relation with math achievement. And so quantile regression helps you more comprehensively evaluate for whom the relation between SES and math achievement is strong or weak. So here, if you're between like the 40th and 70th percentiles, the relation, the impact of SES is much stronger than what OLS would suggest. Comparatively, if you're below the 15th percentile or above the 80th percentile of math achievement, the OLS estimate is stronger than what it actually is. It's an overestimate. So this kind of gives you a sense for how quantile regression can better unpack the dynamic relations of what's actually happening in your data. A few quick things in terms of showing, well, that's great. That's appearing on my R window. What can I actually do to use this? You can use the sync command, which is basically creating a text file, and it will produce the object that you want in some type of output. So if you run those lines, what you essentially get is the output generated here to kind of a text file. And so here are all the results there, and you could use, like a block select mode and, copy and paste different values to a table. You could also put this out into a doc. And so if you put it out to a doc, you'll get the same kind of output. It's just not formatted nicely, but it is in a Microsoft Word document. So what's actually a nicer way to do this is if you use Broom and tidyr, what you can actually do is create an object. And in this case, I'm just calling it something, where you just say tidy the object. And if you do that command, and here I'm writing it out to a CSV file called Full Metal Alchemist, you actually get all the results from the quantile regression into something that is much closer to something that you can make a nice APA formatted table out of. So that's using the Broom and the tidyr command. You can be able to get those data exported. Let's see. The other way you can do this is you can use TextReg. But the wonky thing with TextReg is that you can't pass a vector through it. So I can't take QM10 and then just say create a .doc for like a nice APA formatted table. You actually have to run into the individual quantile regressions. So I'll show you what that will look like. If I run, let's say, 3 separate quantile regressions where I have the 0.25, 0.5, and 0.75, then I can use the HTML reg in a .doc file that I'm going to call kind of Alphonse Elric. And what that's going to do is create a Microsoft Word document that has those models summarized in more of an APA formatted table. So you get the intercepts, the slopes, the standard errors, and you get p-values. And you can format this a little bit faster. What's nice about the TextReg command is you can also specify what stars you want to denote what levels of significance. So by default, it does 001, 01, and 05. Here I'm just adding 0.1 in as well. And so if you do that, you can now see, even though there wasn't anything significant at 0.01, it's saying if there is a dot there instead of multiple asterisks, it will give a dot, and the dot would signify that it is statistically significant at a level of 0.1 or less. All right, so last few things I'll show you, and then you can kind of dig in on your own time. Just like you can do multiple regression in OLS, you can do multiple quantile regression where you have multiple predictors. And so you can get estimates and intercepts for SES and minority. You can plot them. So now you have intercept, SES, and minority status. So what you can see here is when you control for minority status, we still get significant differences between our quantile regression estimates of slope for SES and OLS. And so there are still differences here. In terms of minority status, there aren't necessarily, even though there are trends, right? Here's the OLS slope that would say at lower levels of math achievement, the gap is the same, right? The gap is like minus like 3, but the quantile regression says that the gap might actually be smaller at minus, it might be actually half of what it is in the OLS. These confidence intervals overlap. So we might not actually want to say that this estimate or this OLS estimate is a underestimate or an overestimate because the confidence intervals of the coefficients overlap. And the other thing that's very interesting, and I don't know if Keenan is still on now or not, but you actually can plot interactions. And so what's interesting with interactions is that, where is it? Oh, sorry, I need to plot it. Okay, here we go. And I'm actually gonna, let me do this in a way that, all right, here's the interaction. What's fascinating with something like this is that on some levels of the conditional distribution, the interaction is significantly different in quantile regression compared to OLS, and for others it's not, which means when we think about how we explain or unpack our interactions, it may mean along some levels of the conditional distribution of math achievement, we have to understand SES and minority status in context of their dependency on one another. And you have to actually include the interaction, right? You have to interpret the interaction, not the main effects. But for places where the interaction term is not significant, which is right here, you would only interpret the main effects. And so quantile regression includes some complexities in terms of when you're actually unpacking the relations of your independent variables to the outcome, and you're trying to talk about the strength of those relations. Along some quantiles, you have to consider the interaction, and along some you don't. So, quantile regression is still, it's still in its infancy in many ways in education and social sciences. I haven't seen a lot in terms of like what people are talking about in terms of how you unpack this. I've taken a stab at it, but I am a completely imperfect and methodologist, and I don't fully understand these things yet. I'm trying to think about more about them, but right now I'm just trying to do my due diligence and like, how do you report these things and where do we be careful? The last thing I want to show you before we go is that you can statistically compare the slopes that you estimate within a model across quantiles. So if I, going back to the math achievement and minority context, let's say I'm going to do C 0.1, 0.2, 0.3, 4. I'll just put in 0.7, why not? And then, sorry. All right. All right, so we get different estimates. So we might see, down here at the 0.1 quantile, the difference in math achievement between minority and non-minority students is about 3 points. Here it's about 4 points. And at higher levels, maybe it's a little bit higher, of about 5 points. And maybe we'll want to know, well, to what extent are the slope coefficients? Is this gap of 5 points in math achievement at the 0.5 quantile, is that statistically different than this value? Because it could be those points overlap. So you can actually estimate the two regressions separately and say, estimate this relation conditional on the 0.2 quantile, and then separately conditional on the 0.5 quantile. And then you can do an ANOVA. If you do ANOVA of the two objects, this is testing the null hypothesis here it's testing the equality of slopes between the 0.2 and the 0.5 quantile, right? And so the null is that they're equal. And so here we're rejecting the null hypothesis that the two slopes are the same. So we would reject that hypothesis and conclude that these two slopes, the slopes in these two models, the minus 3.89 and minus 5.09, these are statistically differentiated from each other and would thus have meaning. Someone asked a question of how do you determine what quantiles to investigate? That's a very good question. I think it needs to be driven a priori. I tend to do like 0.2 and 0.8, or I tend to look at interquantile ranges. So comparing the 0.25 to the 0.75. I just tend to want to think about it as conservatively as possible. So it's kind of like heuristics. But if you have empirical questions, again, like beforehand, it's like you could compare all different quantiles to each other. What I would say with that, though, and again, this is in its infancy and I haven't seen much about this, is that in the same way for many types of models, when you are looking at multiple hypothesis testing, whether it's causal models or individual differences models, whether you have multiple DVs or multiple comparisons, we look at corrections, right? Whether you're doing Tukey, Bonferroni, or looking at something like a Benjamini-Hochberg correction for false discoveries, I think it is wise to, when you do multiple comparisons, like between quantile analysis, that you do a some type of false discovery correction or some type of multiple hypothesis correction to guard against a false discovery rate when you're comparing a lot of quantiles to each other. There are not rules for that. Hopefully someone here gets intrigued by it and might do a simulation to kind of provide recommendations to the field. I think that is somewhere we need to go. But I think in my mind, the fewer that you test, the more that you think about those contrasts beforehand, and the more that you correct for the number that you do, I think that is at least good due diligence as a methodologist or analyst or data scientist, whatever term you ascribe to yourself. Whatever mantle you take on. I think those are the minimally 3 things that you can think about when applying that. So that is a very brief intro to quantile regression. I know it is hurried, rushed, and confusing. I'm happy to post some other resources. Hopefully, really, I just wanted to give you a teaser for why I think, and that's all of failing at R is just teasers for, hey, R isn't so scary for doing these things. There's a lot more you can do with it. Hopefully with this code and the examples, it has inspired some curiosity that you can do some more digging. Again, post in the meeting chat or otherwise, if you would like more resources, I'm happy to put in videos, both trainings that I've done as well as other excellent methodologists who are better communicators than I am in the channel, so people can really learn. Next week, I think next 2 weeks, we will be doing, we'll do a 2-week overview of multi-level models, and then we're going to do our final 4 weeks in graphing. Next week will be, it might be a little bit shorter, and I may need to do it asynchronous. I need to see, so my family, we're going to the beach for the week. But what I think my toddler, he'll be napping, so it's super easy to do and fun to do something like this. This is fun for me. So I'll get a break from the beach. I'm like Anakin, and I don't like sand, so I'll be in the house. We'll have fun. I'll show you a picture of the beach while I'm there, and looking forward to seeing you all next week. Thanks for stopping by.
Can I ask a question?
Yeah, are you able to see the screen? Because it's freezing out for me again. I don't know what's going on. Anytime I used that plot command, just straight up plot, yep,
my session would crash. It looks like it was trying to sort out, obviously something was churning in the background and it wouldn't run. And so I kept having to restart R during all of this. I mean, I can see your session. I can see the cursor moving. I was trying to figure out if I had a package misinstalled or not, the library not set or something, but I can't find why when we get down to line 160, that area plot QM10 just crashes my whole session.
I'm back.
No, you're fine. No.